Okay, so let's start. Welcome everybody. Welcome to this follow-up workshop on time series analysis for ecologists. My name is Ulrike Obertegger. I'm working at the Edmund Mark Foundation in Italy, and you can see also my email address. I'm responsible for the long-term ecological research site Lectover in Italy. I'm located in northern Italy, close to the border of Austria, and with the red arrow, you see where I'm actually sitting, and this is the landscape around the big city. It's not that big actually, of my home city. So the idea of this workshop is based on this paper that came out in March, so one year ago, and it's a very nice paper that evaluates the importance of change points in time series analysis. And when I read this paper, the figure 1 attracted my attention because there was this example of a time series. You had two areas, the gray one and the green one, and until a certain time, both areas were unprotected, and then the green one changed protection status from unprotected to protected. And they continued monitoring the birds there. And after a certain time, they wanted to know if this change in protection status had an impact on the presence of birds. So I was really interested in this study. And I was thinking, how would I analyze such a type of data? Before starting to do something fancy by myself, I had a look at box 2. And in box 2, as you can see here in this gray, with the gray background, the authors proposed this, this formula. This formula is the value is the bird counts. Bird counts dependent on time. The before and the after is that they indicate what was before and what was afterwards. Then some control intervention variables, some covariate, and then they put all the possible two-way interactions and the three-way interaction. So I was curious actually how this would go with R. So the first step that I did was creating some artificial data. And this is how the plot looks like. And the very naive approach, imagine a friend would give you this data, it would just tell you, please analyze this data. I would like to know if there is some trend. And a naive approach without anything, you would just draw two lines, two regressions, and then you would go to your friend and say, look, there's a straight upward trend for the protected area and one from the unprotected one. But in this case, you would not consider that there was a change in the protection status. So now I would like, the presentation will be a little bit jumping between the PowerPoint and the R script. So now I would like to go to the R script. As usually, I start with remove list. So I will completely remove or delete everything what R has in its memory and also here. Okay. These are the data, how they look like. It's just a year variable, the counts for the unprotected area, the counts for the protected area, and then a variable, actually a factor that indicates the two phases. With set seed is important because in the next two lines, I add some random noise to my data. And if you do not set this set seed, you will, in every run, will get different numbers, and this can a little bit make more complicate the whole analysis. So let's add these random numbers. Then we do a little bit of pivoting. but so that we have just 3 columns, one for the year, for the time, one for the status, and one for the counts. Then we add this phase change, because the nice thing about this data set is that you know when the change point occurred, and finally the plotting. So this is a little bit of change, because I just told you if you do just a linear increase, neglecting the change point, you get a nice linear regression, but actually this modeling is the wrong approach. And why it's the wrong approach? It is the wrong approach because you have at the beginning, let's just for the red line, all residuals are above the line, then all the residuals are below the line, then again a block where all the residuals are above the line, and the residuals for linear regression or for every model you apply, they should behave like bees in the sky or like stars in the sky. There should be no pattern. To convince you, because one thing is saying, the other thing is showing. Imagine we model this as two-way interaction. That means no consideration of this change in a protection status. And we get a nice model. I mean, there are stars everywhere, a high R square, but the thing that you should always do is have a look at the residuals. The residuals in this case are consecutive, as are the observations. And to get the residuals just for the red line, we have to take always the second observations, because in my data set, it's unprotected, unprotected, protected, unprotected. Also, therefore, we also have to take the right residuals. If we do this and have a look if there is temporal dependence, yeah, if you pay attention to this, yes, there is temporal dependence. If we have a look how the residuals behave along the line, you see that you have an area where all are above the line, most are below the line, and also this is an indication for a misfit. The same we can do for the unprotected area, and here you have a clear indication of a temporal dependence. That means that our model is the wrong one. If we have a look again at the residuals, also here you have some residuals that are above the line, below a line, and then again above the line. And this is a clear indication of a misfit. And with this, I should have convinced you that applying this model is the wrong way to go, and you have to do something different. And this something different is modeling this data set considering this change point, okay? And it would look like then, as it's shown here, you have 4 different regression lines because the data set is split into 2 phases. So how can we do this in R? In R, it's done like this. You have here the 3 main covariates: year as the temporal variable, status and OBS for observation. These are the 2 factors, and then all the 2-way interactions, and the last line, the 3-way interaction. A shortcut for this would be, it would be like this. You just put the star, and this tells R that it has to take all the main terms, all the 2-way interactions, and all possible 3-way interactions. But in this case, there's only one 3-way interaction possible. Yeah. So in order to know if the 3-way interaction is really needed, because remember, you want to keep your analysis as easy as possible, not too complex, we do this so-called nested testing. Nested testing means that you use the most complex model as the baseline model, and the next model is the less complex. And in this case, less complex means that you are deleting or not considering the 3-way interaction. So mod 0 is my baseline model. Mod 1 is the model, the less complex model, where the three-way interaction, also this line is missing here. Okay, so mod 1, execute, mod zeros, execute, mod 1, execute, and now it comes to nested modeling. Nested modeling means that we are comparing the more complex to the less complex model. And before I execute it, I will tell you with the ANOVA command, when you find a statistically significant result, this means that you cannot go with the easier model. That means there's a statistically significant difference in both models, and you cannot go with the easier model. So, but let's see it in action. So this tells you that the more complex model is needed to explain this data. If there is nothing statistically significant, then you can go with the less complex model. So summary mode, this is the summary mode. And now we are going, oh no. This is a little, just a moment, I have to, okay, yes, solved. Okay, now we are going back to the PowerPoint. So as this I explained, and now again, you see here the output of from R, where you have all the three-way interactions and you have a lot of output. And what we want to obtain, we want to obtain the regression lines for the 4 relationships here shown in this graph. When I saw the output first, I was a little bit surprised because actually I didn't know what to do with this bunch of information. But we can figure this out, and you just have to remember 2 rules. The first rule is that factors influence the intercept. And you have 2 factors here. Status, that is protected versus unprotected, and OBS, that stands for observation phase 1 and observation phase 2. So these are the factors, and the factors influence the intercept, and they are colored here in blue. The intercept that is stated in the output for R is related to the baseline model. And what is the baseline model? The baseline model is that one to which all other parameters are compared to. And how is the baseline model decided? It can be decided in 2 ways. First, you let do it R. And R does it alphabetically. So when it comes to status, what's the baseline for status? Is it the protected or the unprotected? P comes before U. So the baseline is status protected. What is the baseline for observation? Yes, OBS 1 comes before OBS 2, because when alphabetical order is the same, then R considers the numbers. So our baseline model is this one, is status protected and observation phase 1. This is the baseline model. These are the baseline data for the baseline model. Yeah, so intercept. The intercept that is reported as the intercept is the intercept for the baseline model with status protected and observation phase 1. I think this is the hardest part of the whole thing, that you understand that what is the baseline and everything is referred with respect to this baseline. So now let's try to understand how to get the intercepts for the next model, so for the next linear relationships. Okay, next one. Intercept for status protected, observation phase 2. With respect to the baseline, the thing that is different is this OBS, because we change from phase 1 to phase 2. So we go to our output, okay, intercept. And now we check, here's OBS phase 2. So this 1.2 is the difference with respect to the base, to the intercept of the baseline. So what we have to do, we take the intercept of the baseline and we add this difference, and it's always adding, okay? So this 100 is now our intercept for the model for status protected observation phase 2. The next one is the intercept for status unprotected and observation phase 1. With respect to the baseline model, what is different? It's the status. Status for baseline was protected. Now we're looking the intercept for status unprotected. So again, we take our intercept for the baseline, the 99.18, plus the difference with respect to status unprotected. And this is then our intercept. And now it comes to the fourth one, where everything, the status and the observation phase, are different with respect to our intercept, of the intercept of the baseline model. And here you have to consider the every difference with respect to the baseline model. You take status unprotected, you take the difference with respect observation phase 2 plus also the interaction term. And finally, you have the fourth intercept. And now we have to do the same game, the same exercise for the slopes. The slope is indicated by year, and this is the slope for our baseline model. And the baseline model is again the red one, status protected, phase 1, and everything for the slope is now again reported with respect to the baseline. Slopes are indicated with, also the thing that you have to take into consideration, there is always this year component, year and colon, and then the factor. And this is the thing that should attract your attention. And these are the numbers that we have to consider. Okay, slope for status protected and observation phase 2. Also, remember, baseline, the year component has already the same protection, but we need to change with respect to the phase. So this is the value, this is the difference in slope. So we have to calculate 0.09 plus 0.12, and then we get the slope value. When we change only the status, that means the baseline is for status protected, but we want to have status unprotected. The observation phase remains the same. So again, we take the year, the slope, and we add the difference. In this case, the difference is really negative, but a plus minus stays minus. So this is then a subtraction, and you get this slope. And the last is the most complicated because you have the status unprotected and the observation phase is 2. So it's everything is different with respect to our baseline model. And then you have to add just everything that is reported. So we have here the baseline, we have plus for the status unprotected, plus for the phase observation phase 2, plus this interaction, and so you have the slope. So finally, these are the 4 linear regressions for our for the 4 relationships. Let's jump just a minute to R. The lines I will ignore just for a moment. With CoF, also our model that we are considering is the mode 0. With CoF, you get all the coefficients, And here it's just that you take the right part and do so you take the baseline and you add the required coefficient to get the intercept for the different models. So here I did it step by step, and when we execute all those lines, we get the same numbers as I showed on the PowerPoint. Now I want to show you a tiny plot, but before this expand grid, I would like to explain this, because with this we just are creating a data frame and with this data frame we are predicting values, and we are predicting values for unprotected, protected, phase 1 and phase 2. We are protecting for the smallest and the highest value of time, 1 and 30, and for 0. And you will immediately understand why also 0. So let's execute this as just creating this data frame with predict pred. So we take our model and we predict for the values from the pred data frame. We get our counts. And now we want to do some plotting. And in this plotting, I want to show you what exactly the intercept means. The intercept is here. The intercept is the value when the regression intersects with the y-axis. And for phase 1, this difference in the intercept is much larger than for phase 2. Another thing here, I hope you noticed it, that in the original paper, time was indicated with a year number, 19 something until 2000 and something, but I did not really code the years as year, but I coded them as a consecutive number. And this because you have always to remember that in R, the intersect, or when you treat with yearly numbers in R, the 0 intercept is 1970. And in order to avoid this problem that what is the intercept, I decided that instead of starting with 1990, let's start with 1, 2, 3, 4, 5, and then go on. And afterwards, when I really needed that we have here indications of the years, then we could put it back. But from a modeling perspective, sometimes it's easier to put just a consecutive number and not to put the proper year numbers. Okay, so this was just an excursion why I put here the year numbers and not the normal integers and not the year numbers. For the slopes, you can find here the codes, and also these give the same numbers that are shown in the PowerPoint. Okay, PowerPoint. Oh, yes. Okay. So now that we got four nice regression lines, I think the next question that should come to our mind, at least it came to my mind, was, are those 4 relationships really statistically significantly different? And to answer this question, there are 2 options. And the easiest answer to this question is to use library EM-means. Library EM-means is the library after LS-means, if somebody already knows it. And this does post hoc testing. It's your best friend if you want to do post hoc testing for linear trends and for ANOVAs. So with LM-means, the only thing that you have to do, you have to split the data in the 2 periods for phase 1 and for phase 2. I show you here, you did this with tidyverse. We filter from our data the observations for phase 1, and then we execute again a linear regression. And in this time, This is year star status. This means two-way interaction. You do the same thing for the phase 2. And so that we have two data sets for the observation phase 1, observation phase 2. And we want to know if the slopes of the those two relationships are statistically significantly different or not. Let's see how this is done in R and what's the output. So as I told you, here are the 6 lines. Everything is fine. We call library EM-means that does post hoc testing. And this is the line, the code for testing if the trend is different. You call the model. You say that you're pairwise testing for status, and our trend variable is the year, because this is our continuous variable. You execute it and you get some output, and you can also execute it and you get again some output. To explain this better, okay. And here is the output. So the output tells you 2 things. First, it gives you the slope for the protected and for the unprotected relationship. And the slopes are, I would say, the same as estimated with our three-way interaction model. But the thing we are interested is this part, because here it's testing if the slopes are statistically significantly different. If you look at those 2 slopes, they're quite similar, but who knows? It could be that the error of those slope estimates are so small that they do not overlap. But in this case, we see that you cannot discriminate between those 2 slopes. They're essentially the same. Then when we look at phase 2, as phase 2, I mean, just by looking at the relationships, okay, there's not really statistics needed that you can tell that they are different. But in any case, to be complete, you should test it. You should show your readers that the relationships are different. So again, the first part tests the slope estimates. And the last part here, the contrast, with the contrast, you are comparing the 2 slopes. And of course, you have a highly statistically significant value. This means those 2 slopes are really different. Okay, so the second possibility how to test if the slopes are statistically significant different, there is also the option to use confint. Confint gives you confidence intervals. And remember, when a confidence interval includes 0, then the parameter estimate is uncertain and the estimate is not statistically significant. For our model, we have 2 occasions for OVS phase 2, where this is the case, and for this 2-way interaction. But honestly, I did not know what to use with this information. But for this, we have library EM-means that does a great job in post hoc testing. So another thing, now that we have this nice model, we should check if we modeled correctly the change point, if there is no misfit. And for a linear regression, what is misfit? Misfit would be that we have autocorrelation in the residuals, or that we have heterogeneity. And what is heterogeneity? Heterogeneity means that the variance of the residuals for the different factors is not the same. How can we do this? We take our residuals from the model. And here's a tricky part that if you downloaded the old manuscript, the old script from the old R script from the website, then I had to change the script a little bit, because you have to consider here that the residuals are consecutive And my data are also consecutive, where I was jumping from protected, unprotected, as that protected and unprotected are alternating. Therefore, also the residuals, we have to take the right residuals for inspecting the residuals of the different relationships. So it's not that you can just take the residuals and then write autocorrelation function. So we create a new frame. And for your better understanding, what is this frame? This frame are the residuals here. You have the year column, you have the status column, and you have the count columns in OBS. And now you see that we have to take the right residuals for making our considerations about heterogeneity and temporal dependence. So I know that the first 30 observations are for phase 1. So I take the first 30 observations. This is my frame phase 1. And I take the residuals only for unprotected, and unprotected is the green. So these are my resi 1. These are the residuals for this line. And what do we want to see? We want to see no temporal correlation. We want to see no difference in the variance of residuals with respect to our factors. So autocorrelation. Okay, this is safe because the autocorrelation does not go outside the blue bands. And the blue band, everything that goes outside the blue bands means that there is autocorrelation, and we don't want to have autocorrelation. Then we do box plots, and this is the but wait. Yeah, actually, this is not richtig. Okay, this is not fully right, as I realize now, stupid from my side, but I will not teach you something wrong. Therefore, I will tell you what is wrong here. With Resi, I took the residuals, I took those residuals, so there is no way actually to test if they have the box, if there is heterogeneity. With just testing for temporal correlation, we are safe, but I could take nothing. If we take these residuals, yes, so it's just taking those residuals. I excuse everybody for this little error. Okay, this I have to fix, but I will tell you again. So what did I mess up here? We want to check if the residuals from the green line and from the red line are the same or not. Okay, and for this I have to take the residuals from phase 1, and then I will have to do the box plot. Okay, so here just note I have to fix this, and when you take it from the website it will be fixed. Okay, so let's write here. So take the residuals from phase 1 and plot versus all factors. And there you don't want to see any sign of heterogeneity. Okay. Now that we did this, and let's say actually this was following blindly the approach that is shown in this paper. It was a nice exercise for understanding what a three-way interaction term does, how we have to interpret it. But with this approach, you have to know where the change point occurred. It's easy to know in this case because there was a change in the protection status, but imagine that something else changed this data set. Imagine somebody gives you this data set, nobody remembers this change in protection status, so you really don't know where the change point occurred. And for such circumstances, we have a library struct change that tests for a change point in our data set, in our time series. Okay, so here we go. Here we have library struct change. We load it. And the library struct change deals with time series data. So I converted this to a time series. And I did not mess around with putting here 1990 something. It's just start with 1 and it's yearly data, so frequency is 1. So we make out of these observations time series. And we do this only for the protected area. So we are doing this only for the red lines or for the red points. Okay, so if we call count protected, you see it's a time series. It starts with year 1, it finishes with year 30, and its frequency is 1. So these are yearly data. Then we can get the time component of our time series. And again, you see it's 1 to 30. So with f-stats, here comes the real line for investigating a change point. And then we are plotting it. And it's not a surprise that this is highly statistically significant, because these are data that I generated, but that's not that important. In any case, it's clear that here is something going on. We can also then get the p-value for this estimate of the change point. Then, once we know that there is a change point, we have to estimate it and to get also confident intervals for it. It says that the change point happened around the year, the breakpoint 15, and it has some confidence interval. Now it comes a nice thing, because with CoF from breakpoint, you already get the intercept and the slope for the two relationships. And I hope you can remember that you can recognize the 0.22 that we already had from our three-way interaction model. But here, this is a little bit different. The stupid thing here is that we do not get any p-value, any stars for the single parameter estimates, okay? Therefore, we have to go back and do again linear modeling. And in order to do so, we have to extract the segment. That means the factor that is based, the splitting of the data set based on the recognition of the breakpoint. As a segment 1 is the data set before the change point, and segment 2 is then the second part based on the indicated change point. Now, in the 3 lines, I wanted to show you 3 different possibilities how to model the same thing. With the first line, you should recognize the normal coding. This is a two-way interaction. Then there is something different, sec/year prot, and then the minus plus sec/year protection. Okay, all 3 models give the same information, but in a different way. And if we execute this, you will notice that there are some differences. Okay. So here we have side by side the 3 different approaches for getting the information. So this is the normal two-way interaction. You should recognize the intercept for our baseline model. You should recognize the slope. So those 2 are our first model. And for the second model, you have to do the game of, or the tactics, intercept plus the difference, also intercept plus segment 2 is the intercept for the other model. And for the slope, you take year prot plus this this number 0.12, because this again is the difference to the baseline model to get the slope. If you do it like this segment slash here plot, you should see that now the line for the slope is completely different. You have immediately, it gives you immediately the slope for the first segment and the second segment. You don't have to do any calculations by yourself. It's just for the intercept that you have to do the calculations. And now, if you do it like this, the -1, with the -2, you get immediately the whole output. There is nothing to do in calculation. The -2 tells R that there is no baseline testing for the intercept. And the SEG slash tells R that there's no baseline testing for the slope component. These are the three possibilities that sometimes you will find. But I think the safest thing is always to do the normal coding, because then you, at least I'm not getting them completely confused. In any case, there are three possibilities, and all those three will lead you to the same information. Okay, now let's again have a look at my residuals. But the residuals again have here, okay, the residuals do not show any sign, and these are the residuals that are consecutive, but they do not no, this is fine, this is perfect, this is okay, because here we only have one line actually. So let's plot it. So actually we are looking at this should work, that the residuals, when they are consecutive, do not show any pattern. We could also split the residuals here and then see for the different lines if they don't have any pattern. In any case, it looks quite good, because also if you do visual inspection, yeah, okay, this should work. The same thing now is done for the unprotected area. And this means doing the time series, getting the year component, doing the testing, and plotting it, the 4 lines. Okay, so here's highly statistically significant. We are doing the test. You get also the change point is highly statistically significant. We're trying to estimate where the breakpoint is. Now it's at 0.16. So you see, before it was at 0.15, if I remember well. Yeah, you know, 15. But for the unprotected, the estimate is now at 0.16. Then we can have a look at the coefficients. And here you can get the estimate of the intercept and the slope. And these are the 2 slope components. But remember, you do not have any p-values. So again, we are doing linear regression. And here is something that surprised me a lot, because you have the intercept for the segment 1 that is highly statistically significant. You have the slope for the segment 1 that is also highly statistically significant. But the next model, as the segment 2, the estimate for the slope and the estimate for the segment are not statistically significant. And this is something that wonders me a lot, because the model per se says, okay, you have some data, there is a change point. You have some data where we can estimate slopes and intercepts. We know that the estimates for the first segment, they are all okay, highly statistically significant, but when it comes to the second part, they are not. So when we plot this, it's looking like this. It looks like this. This means this is the part where we are highly confident in the estimates of our data, but here we are not. So as an answer or as another try to answer why it is like this, I was thinking, what about if this is a shift in the mean? Shift in the mean, what does this mean? That means that here there is no trend. It's just a mean. It's a fluctuation around the mean. Then our change here happened, something happened here. And then it just jumps down, and then again it fluctuates around the mean. To compare the two models, we can use the root mean square error. The root mean square error can be calculated with the library RMESC with this command, root mean square error. And you just have to provide the observed and the fitted value, and will calculate everything for you. So the root mean square error with regression, considering here the change point, is 0.4. But now let's do, before I wanted to do, okay, segmented regression. Segmented regression is I would call it the brother to structure change. It's also that it tests for linear regression, and it tests for change points in linear regression, but it's not that powerful as it's segmented, but you can also give it a try and see how it works out. So as a first segmented regression, okay, library segmented, we plotted, this is how it looks like without any knowledge about the change point. You put in the code LM, and then here comes the part for segmented. This means our model is O. The dependent variable is year unprotected because the year variable. With the psi command, you give an estimate of a possible change point. O segmented. And then with summary, it will tell you that here you have estimated breakpoint, and here it puts it at observation 11. And remember that struct change put it at observation point 16, but segmented put it at observation 11. So there is quite a difference. When you do segment summary, you will never get any p-value for the second slope, okay? Never ever, because it's not implemented in segmented. And if you do confident, you get again this confidence interval for the breakpoint, and they are quite large, 5 and 16. So if we then want to have our root mean square error for segmented regression, it's 0.55. So with struct change, it was 0.43, but segmented regression is already higher. So segmented regression is not the way to go. Now, finally, what if this is not regression, but a shift in the mean? And we can, this shift in the mean, parameterize with this. We put the observed values, the count, and dependent on 1. And dependent on 1 tells R that it's just a shift in the mean. So again, it says, okay, after 15, there is this change point. The p-value is highly statistically significant. The breakpoint, where is it? Now it's something that is quite surprising also here. Instead of indicating one change point, it indicates 2 change points. Probably because you have 2 peaks here. But you can force breakpoints to just find 1 if you write breaks equals 1. So if we do this, you get 1, and the breakpoint is again around 16. And this is quite agrees with what we know about the data set. If we inspect these, you get 2 different intercepts, and this means that the first intercept is higher than the second one. And when we do linear regression, but we tell R that this is just a shift in the mean, you can get here the p-value. So everything is highly statistically significant. Now we can plot this. And here you have The blue line is the shift in the mean. This cyan line or blue, clearer blue is the segmented regression. No, it's the structure change. So these are the differences how the data can be seen. And with the root mean square error, we can compare all the three models. And now, based on the root mean square error, who is the winner? Yeah, finally the winner actually is structure change. Structure change that says that there's clearly increase in the data until the change point, but then the estimate is quite insecure. And now it's time, I guess, to go back to the original data and have a look to the original data, because these data are fake data. I mean, not really fake data. These data are data that I created based on a certain expectation. And it's time to go back and see how I created this data. If Excel lets me do this. Come on. Just, okay, now it's possible. So here you see my data that I created. And I created them with the strategy that I wanted to have both for phase one, I wanted to have an increase. So for both for unprotected and protected, you see that the slope is 0.1. It's just for that for the protected area, I took this value, but I decreased it for one observation, for one unit. So here in both unprotected, there should be a clear increase. For the phase two, what I did is for the unprotected, actually, I decreased the slope, while for wait, where are we? Nope. No, I'm in the wrong column. While for the protected, you see the slope is 0.2. So for the protected area, everything is fine. The problem comes with this thing here, also with the phase two unprotected, where my parameterization was to decrease the slope, and then by adding this random noise, as you can see here, probably I completely decreased the trend in this part, and so the whole analysis gets a little bit more tricky. Yeah, the final lines of this code, they say, play with the standard deviation and see what happens and have fun. Before you can have fun, I have to correct the issue with the residuals. In any case, I hope you enjoyed this workshop, you learned something. And if you have some questions, I'm happy to answer them.